The following program is brought to you by Caltech.
Okay, good evening. Welcome to this great occasion of having the annual De Prima lecture being given by one of our own, Tom Apostol, who's recently turned 90, and bespeaks the truth of all that we've heard about the Greeks living long. So, he's a really great person, and I've been here 24 years, and he's always been very friendly, and ever since I got here, he's been extremely nice, and his books, of course, are really great. Like when I was in high school, I was learning some calculus, and I thought long ago that I knew everything until somebody gave me a copy of his book and said, read this and see if you can follow it. And that was a challenge, but it was great, and later I got to read several of his books, like Analytic Number Theory, Dirichlet series, among others. And I know a lot of people here have been influenced by his books, and he's a great speaker. So, without much further ado, I'll invite Professor Apostol to give his speech, his lecture on the title is The Geometrical Snapshots from Ancient to Modern Times. Thank you.
Thank you, Diniger. Mathematicians are attracted to mathematics by surprising patterns, elegant theorems, ingenious proofs, and a whole world of exciting ideas that have inspired and challenged the human spirit for centuries. This talk treats a collection of geometric ideas that evolved from ancient times to modern times, specially chosen to demonstrate the effectiveness of appropriate visual representation of these ideas. We begin with some landmark geometric discoveries of Archimedes, the greatest mathematician of ancient times, who lived from 287 to 212 BC. Although Archimedes was also a physicist, engineer, and astronomer, his most profound contributions were to geometry. The story of how we learned about Archimedes' discoveries is both interesting and lengthy. Rather than dwell on this story, I have prepared a brief summary in this handout for you to take as an appendix to this talk. Archimedes was aware of Euclid's elements, which appeared around 300 BC, so he knew how to find areas of polygonal regions and volumes of pyramids, cones, prisms, and cylinders. For example, the volume of a prism is the area of its base times its altitude. The volume of a pyramid is 1/3 the area of its base times its altitude. The volume of a cylinder is the area of its base times its altitude. And the volume of a cone is 1/3 the area of its base times its altitude. Therefore, the ratio of volumes, pyramid to prism or cone to cylinder, is 1:3. Archimedes was the first to find the area of a circular disk. Euclid knew that the area of a circular disk is proportional to the square of its radius, and that its circumference is proportional to its diameter. But Archimedes was the first to show that the constant of proportionality is the same for both area and circumference. This constant, that we now call pi, is defined as the ratio of circumference to diameter. Today, every young student learns that the area of a circular disk of radius r is pi r squared. The expression pi r squared, which is written in modern notation, does not appear in the works of Archimedes. He discovered an equivalent result expressed as follows. The area of a circular disk is equal to that of a rectangle having one edge equal to the radius of the disk and the other edge equal to half its circumference. This statement is typical of the style of Archimedes. It relates the area of a curved figure to that of a simpler figure, a rectangle in this case. The idea behind Archimedes' proof is demonstrated by the following diagram. The circular disk is divided into an even number of radial slices, which can be rearranged to form a figure that is very nearly a parallelogram with the same area as the disk. As the slices become thinner and thinner, the parallelogram becomes more and more like a rectangle, whose base is half the circumference of the disk and whose height is the radius of the disk. So the disk and rectangle have equal areas. Here's an animated version of this idea. Another profound achievement is Archimedes' calculation of the area of a parabolic segment, the shaded region in this diagram, which shows that the parabolic segment fills less than 1/2 the circumscribing rectangle. Archimedes discovered that it fills exactly 1/3 the rectangle. His proof is complicated, but this diagram shows a much simpler proof. We divide the rectangle into 3 pieces that have equal areas, so each piece has area 1/3 that of the rectangle. This proof, and several other geometric proofs of this fact, can be found in our book, New Horizons in Geometry, which my colleague Mamiko Manatsakanin and I published less than a year ago. Archimedes used his style of comparison in treating volumes and surface areas of solids with curved faces. One of his most famous discoveries is that the volume of a sphere is 2/3 that of a circumscribing circular cylinder, and that the same ratio holds for the surface areas. Archimedes was so proud of this discovery that he wanted a sphere and a circumscribing cylinder engraved on his tombstone. I'd like to dwell somewhat on Archimedes' tombstone result. First, he discovered the 2/3 ratio between volumes by performing an incredible balancing act with an imaginary set of scales, placing slices of a sphere and cone on one side and slices of a cylinder on the other, using centroids and the principle of the lever, which were also among his great discoveries. Then he used the method of exhaustion to prove rigorously that 2/3 is in fact the correct ratio for volumes. He used an entirely different method to prove that the 2/3 ratio also holds for surface areas. Instead of explaining the arguments of Archimedes in detail, I will describe 2 simpler arguments that are presented in our new book. Our first argument is based on the following principle, which we call the slicing principle. 2 solids have equal volumes if their horizontal cross-sections, taken at any height, have equal areas. This statement is often called Capillaries Principle in honor of the 16th century Italian mathematician Bonaventura Cavalieri, who attempted to prove it for general solids. Archimedes had already used it 19 centuries earlier for special solids. Here's an example illustrating the slicing principle. These 2 solids have equal volumes because the horizontal cross-sections at any height have equal areas. To convince yourself that the volumes are equal, slice the 2 solids into very thin horizontal slices as shown here. Each slice is very nearly a cylinder whose volume is the area of the base times the thickness of the slice. So 2 cylindrical slices of equal thickness with bases of equal area will have equal volume, and therefore the same is true for any solid built up by such slices. As the thickness of each slice approaches 0, we obtain the slicing principle. Now let's see how the slicing principle leads to the Archimedes tombstone result for volumes. This diagram shows a hemisphere next to its circumscribing cylinder, whose radius is equal to the altitude. Drill a cone with the same altitude out of the center of the cylinder. The cone has volume 1/3 that of the cylinder, leaving a punctured cylinder with volume 2/3 that of the cylinder. Now, slice the full sphere and its punctured cylinder by an arbitrary horizontal plane parallel to the base. It is easy to show, using the Pythagorean theorem, that corresponding cross-sections, the disk and annulus, have equal areas. So by the slicing principle, the sphere and punctured cylinder have equal volumes, which is 2/3 that of the full cylinder. This proves Archimedes' Tombstone result for volumes. What about formulas? For a sphere of radius r, the cylinder has base of area pi r squared, altitude 2r, and its volume, base times altitude, is 2 pi r cubed. 2/3 of this gives 4/3 pi r cubed for the volume of the sphere. But this argument tells us nothing about surface areas. Now I will present a second type of argument that yields both the 2/3 volume and 2/3 surface area relation in the Tombstone result. This argument uses another concept we call the balance revolution principle. Actually, there are two such principles, one for volumes and another for surface areas. The balance revolution principle for volumes states, if the areas of two plane regions are in equilibrium with respect to a balancing axis, then the solids of revolution generated by rotating them about the balancing axis have equal volumes. This is illustrated in the diagram below. To say that the area of the plane regions are in equilibrium with respect to a balancing axis means that the two areas have equal moments about the axis, the moment being the product of the area of the region times the distance of its area centroid from the axis. The balance revolution principle is a simple consequence of a theorem of Pappas, a Greek mathematician who flourished in Alexandria around 300 AD. Pappus' theorem for volumes of revolution states, the volume of revolution swept by a plane region is equal to the area of the region times the circumference of the circle traced by the area centroid of the region. If the area of the region is A and its centroidal distance is C, the circumference of the circle traced by the centroid is 2 pi c, and the volume V is 2 pi ca, or 2 pi times the moment ca. So equal moments imply equal volumes, and we get the balance revolution principle for volumes. By the way, if you know V and A, you can use Pappus to find the centroidal distance c. It's simply V divided by 2 pi a. In this example, a semicircular disk of area 1/2 pi r squared generates a solid sphere of volume 4/3 pi r cubed, which gives a centroidal distance c equals 4r over 3 pi for the semicircular disk. There's also a famous theorem of Pappus for surface areas, analogous to that for volumes. Pappus' theorem for surface areas of revolution says, the area of a surface of revolution swept by a plane curve is equal to the length of the curve times the circumference of the circle traced by the centroid of the curve. In this example, a semicircular arc generates the surface of a sphere. In general, Pappus' theorem leads to a corresponding balance revolution principle for surface areas. If two plane curves are in arc-length equilibrium with respect to a balancing axis, then the surfaces of revolution generated by rotating them about the balancing axis have equal areas. Arc-length equilibrium means that the corresponding moments are equal, where now the moment of an arc is its length times its centroidal distance from the axis. Now look at this diagram, which is from our book. Figure A shows an isosceles right triangle and a semicircle inscribed in a square, with the vertical axis through the center, indicated by the arrow, and with two horizontal chords at the same but arbitrary level. The centroid of each chord is at its midpoint. A simple use of the Pythagorean theorem shows that the lengths of these chords are in balance with respect to the vertical axis. In other words, the length of the chord times the distance of its centroid from the axis is the same for both chords. By taking the union of all such chords, we can build the two shaded regions in figure B, which are now in area equilibrium with each other. Archimedes knew about this area equilibrium, but he used it for a different purpose. We shall use it to prove his Tombstone result for volumes. Rotate these balanced areas around the balancing axis to produce a punctured cylinder and sphere shown in this diagram. The triangular region sweeps out the punctured cylinder, and the semicircular disk sweeps out the solid sphere. By the balanced revolution principle, the punctured cylinder and sphere have equal volumes. Now, the two cones removed from the cylinder have total volume 1/3 that of the cylinder. So again, we see that the volume of the sphere is 2/3 that of the unpunctured cylinder. Thus, we get the Tombstone result for volumes. To relate surface areas, look at part C of the following diagram. There's a nice surprise in C that Archimedes would have been pleased to learn about. The semicircular arc and the vertical base of the triangle are in arc length equilibrium. I'll show you why in a minute, but first let's use this to deduce the Tombstone result for surface areas. The next figure shows what happens if you rotate the semicircular arc and the vertical base of the triangle around the balancing axis. The semicircular arc traces out the surface of the sphere, and the vertical base traces out the lateral surface of the cylinder. So by the balanced revolution principle for surface areas, the surface area of the sphere is equal to the lateral surface area of the cylinder, which is that of a rectangle obtained by unwrapping the cylinder. You want formulas? If the sphere has radius r, the unwrapped rectangle has base 2 pi r, altitude 2r, and area 4 pi r squared. So the sphere has surface area 4 pi r squared. This is 2/3 of 6 pi r squared, the total surface area of the cylinder, which includes the top and bottom faces, each with area pi r squared. Therefore, we get Archimedes' Tombstone result for surface areas. Once again, the area of a curved figure is equal to that of a rectangle. By the way, the area of a sphere can also be deduced from its volume. Take a thin spherical shell, like the skin of an orange. Slice the shell into thin pieces by making cuts from the north and south poles to the equator, and unwrap it so it is nearly flat. You get a solid whose volume is the area of the skin times the thickness of the shell. If the shell has outer radius r and inner radius a, its volume is the difference of spherical volumes, or 4/3 pi times r cubed minus a cubed. The difference of two cubes factors into r minus a times r squared plus ra plus a squared. The factor r minus a is the thickness of the shell. So the area of the base is the other factor, 4/3 pi times r squared plus ra plus a squared, which approaches 4 pi r squared as a approaches r. In the language of differential calculus, we've just shown that the surface area of a sphere is the derivative of its volume with respect to its radius. Now I'll show you why the semicircular arc in part C of this figure is in arc length equilibrium with the vertical base of the triangle. Look at this diagram. It shows a line segment of length L tangent at its midpoint to a circle of radius r, together with its projection of length h, which is a vertical tangent to the same circle on the other side of a vertical axis to the center, indicated by the arrow. The diagram on the right shows that L cosine alpha equals h. Multiplying by the radius r, we find LR cosine alpha is RH, or CL is RH, where C equals R cosine alpha is the centroidal distance of L from the axis. This equates moments of lengths L and H about the balancing axis. So the tangent of length L is in arc length equilibrium with this tangential projection of length H. This figure shows a regular polygonal arc, each of whose edges is tangent at its midpoint to the same circle. We call this a regular circumgon. The figure also shows the vertical tangential projection of this regular circumgon on the other side of the axis. Because each edge of the regular circumgon is in arc-length equilibrium with its tangential projection, we obtain the following theorem. A regular circumgone, including the limiting case of a circular arc, is in arc-length equilibrium with its tangential projection. The diagram below shows several circumgones in arc-length equilibrium with the tangential projection of given height h, including circular arcs, which are limiting cases of circumgones. By rotating each regular circumgone and its tangential projection around their balancing axis, we obtain the following theorem. The lateral surface area of revolution generated by a regular circumgone, including the limiting case of a circular arc, is equal to that of the circumcylinder whose height is that of the circumgone. Examples are shown in the diagram below. All these surfaces have area equal to that of a cylinder, 2 pi rh, where r is the in radius of the circumgone and h is its total height. Special cases are spherical zones of height h. A spherical zone of height h is the portion of a spherical surface cut by two parallel planes at distance h apart. All spherical zones of height h have area 2 pi rh. The next figure below shows special cases in which the circumgone is half a regular 2n-gone rotated about a vertical diameter of the incircle. We call these right circumgonal surfaces of revolution. For these, we have h as 2r, 2 pi rh is 4 pi r squared, so we obtain the following corollary with some examples. All right circumgonal surfaces of revolution within radius r have height 2r and lateral surface area 4 pi r squared. Thus, there are infinitely many surfaces of revolution that share the Archimedes tombstone result for areas. There are also infinitely many solids of revolution that share Archimedes tombstone result for volumes. The following figure shows how concentric regular circumgones and their tangential projections can be used to produce circumgonal regions that are in area equilibrium. By rotating two circumgonal regions in area equilibrium around their balancing axis, we produce two punctured solids of revolution with equal volumes. The next figure shows regular circumgonal regions of equal altitude h in area equilibrium rotated to generate punctured solids of revolution of equal volume. They illustrate the following theorem. The volume of a punctured circumsolid generated by rotating a circumgonal region is equal to that of the punctured circumcylinder whose height is that of the circumgone. The special cases shown in the next figure illustrate the following corollary, which generalizes the tombstone result for volumes. All punctured right circumsolids of revolution within radius r have height 2r and volume 4 pi r cubed over 3. Before going on to other topics, I would like to make some concluding remarks about Archimedes' tombstone result. These days, it is natural to ask if there's an extension of the tombstone result to n-dimensional space. Both the concept of sphere and cylinder have been extended to n space. In 3 space, a solid cylinder can be generated by translating a circular disk, which is a 2-sphere, along a line in 3 space. By analogy, an n-dimensional cylinder is defined as the object you get by translating an n-1 dimensional sphere along a line in n space. Formulas are known for the volume of an n-sphere and of an n-cylinder, but no simple rational ratio relates them, except when n equals 3. In chapter 13 of our book, we show how to extend the tombstone result to n space for every n, including n equals 2. First, you have to replace the cylinder by another object that we call a cylindroid, which is an ordinary cylinder if n is 3, but an entirely different object if n is not 3. Remember, an ordinary cylinder in 3 space can be generated by translating a circular disk, a 2-sphere, along a line in 3 space. But there's another way to generate such a cylinder. If you start with a rectangle, which is the 2-dimensional cylinder, and rotate it in 3 space about one of its edges, you also produce a cylinder. By analogy, you can start with an n-1 dimensional cylinder and rotate it in n space about one of its edges. You get an object that we call an n-cylindroid. When n is 3, this is a classical cylinder. But when n is not 3, it is an entirely different object. We can't draw pictures when n is bigger than 3, so let's look at this figure, which treats the case n equals 2. In part A, we start with a 1 sphere, which is a line segment, and translate it in 2 space to get a rectangle, which is a 2 cylinder. In part B, we start with a 1 cylinder, which is also a line segment, and tumble it, that is rotated about one end. You get a 2 cylindroid, which is a circular disk, not the same as a 2 cylinder. Animation shows the difference. This shows that a 3 cylindroid is the same type of object as a 3 cylinder. This one shows that a 2 cylindroid is a disk, not a 2 cylinder. In chapter 13 of our book, we relate both the volume and surface area of an n-cylindroid with those of an n-sphere. We get the following delightful result, suitable for engraving an Archimedes hypertombstone. The hypertombstone theorem says, part A, the volume of an n-sphere is 2 over n times the volume of its circumscribing n-cylindroid. Part B, the surface area of an n-sphere is 2 over n times the total surface area of its circumscribing n-cylindroid. So in n space, the Archimedes ratio 2/3 gets replaced by 2 over n. In particular, when n equals 2, this ratio is 1, because the 2 sphere and the circumscribing 2 cylindroid are identical. What could be simpler? Now I'll turn to some interesting geometric objects the Archimedes would have enjoyed but did not consider. The first example is a cycloid, the path traced by a point on the boundary of a circular disk that rolls along a straight baseline without slipping, as shown here. The shaded region obtained by one complete rotation of the disk is called a cycloidal arch. This curve has a long and rich history going back to the 17th century, when it attracted the attention of many scientists and mathematicians. For example, Mersenne, Galileo, Torricelli, Roberval, Huygens, Leibniz, and Johann Bernoulli. Mersenne tried, without success, to find the area of the arch and posed the area problem to others. This diagram shows that the area of the arch is less than that of the circumscribing rectangle, whose base is the circumference of the disk. If the disk has radius r, its circumference is 2 pi r, the base of the rectangle, and the altitude of the rectangle is 2r, the diameter of the disk. So the area of the rectangle is 4 pi r squared, which is exactly 4 times the area of the disk. On the other hand, these two right triangles, which fill out half the rectangle, lie inside the arch. So the area of the cycloidal arch is somewhere between 2 and 4 times the area of the disk. This suggests that it could be that the area of the arch is about 3 times that of the disk. Could it be exactly 3 times? To test this hypothesis, Galileo cut a cycloidal arch of 3 circular disks out of sheet metal and weighed them. He found that 3 disks were heavier than the arch and concluded that the area of the arch is less than 3 times the area of the disk. But, as is often the case with physical experiments, there was intrinsic experimental error. A few years later, one of Galileo's students, Torricelli, proved that the area of the arch is exactly 3 times that of the disk, a discovery that was made independently by Roberval. Now I'll show you why the arch has area 3 times that of the disk. The region above the arch and inside the circumscribing rectangle is called a cycloidal cap. In this animation, the disk is divided into thin wedges by chords emanating from one point. In our book, we show that these wedges can be rearranged to fill the cycloidal cap as they become thinner and thinner. Thus, the cap has the same area as the disk. The rectangle has area 4 times that of the disk, so if you take away the cap, the cycloidal arch that remains has area 3 times that of the disk. The animation is an application of Mamikon's sweeping tangent theorem that I will describe a little later. The factor 3 reflects a much deeper property of cycloidal sectors revealed in this figure. It shows various stages of rotation of the disk, together with the cycloidal sector OPC, bounded by arc OP of the cycloid, and 2 line segments OC and PC. At each stage, we have the following relation, which Mamikon and I first published 4 years ago. The cycloidal sector, OCP, has area 3 times that of the overlapping circular segment cut from the rolling disk by chord CP. In other words, at each stage of rotation, the area of the dark blue region inside the circle is always 1/2 the area of the larger adjacent region. The proof, which is entirely geometrical, that is, without calculus, can be found in Chapter 2 of our book. Further contributions related to areas of special regions under a cycloidal arch were also made by Huygens, Leibniz, and Johann Bernoulli. As a companion to their results, we offer our own contribution as an exercise for the reader. The shaded curvilinear cycloidal region has the same area as the square. The cycloid is the limiting case of a cyclogon, a curve traced by the vertex of a polygon that rolls without slipping along a straight line. Here are some examples traced by regular polygons. Traced by a triangle, traced by a square, and traced by a hexagon. Each cyclogon is made up of a succession of circular arcs, each of different radii. Surprise! A remarkable relation gives the area of each regular cyclogonal arch. The area A of a regular cyclogonal arch is equal to P plus 2C, where P is the area of the rolling polygon and C is the area of its circumscribing disk. A geometric proof without calculus can be found in Chapter 3 of our book. Note that a cycloidal arch is the limiting case when the number of polygonal edges tends to infinity. Then P becomes C, and the formula gives A equals 3C. We have also calculated, without calculus, the arc length of a regular cyclogonal arch. The result is as follows. The arc length L of a cyclogonal arch traced by a vertex of a rolling regular n-gon is given by the formula L equals 4D times pi over 2n cotangent pi over 2n, where D is the diameter of the circle that circumscribes the n-gon. The factor pi over 2n cotangent pi over 2n that multiplies 4D is surprisingly close to 1, even for small values of n, as shown in this table. When n tends to infinity, this factor tends to 1, so L tends to 4D. Thus, the arc length of a cycloidal arch is 4 times the diameter of the rolling disk, a result first proved by Sir Christopher Wren, the architect who designed St. Paul's Cathedral in London. So the area of a cycloidal arch is 3 times the area of the rotating disk, and its arc length is 4 times the diameter of the disk. All these results concerning cycloids and cyclogons can be generalized by considering curves traced by a point on a circle rolling along the outside or inside of another circle, or the vertex of one polygon rolling along the outside or inside of another polygon. 2 simple examples are shown in the following diagram. The curve on the right is called a cardioid, traced by a point on a circle rolling around another circle of the same size. The one on the left is a cardiagon, traced by the vertex of one square rolling around another square of the same size. In Chapter 3 of our book, you will find formulas for areas and arc lengths associated with many examples of such curves, all obtained without calculus. Now I'd like to talk about Mamicon's sweeping tangent theorem and some of its applications. I'll start with sweeping tangents of constant length, shown on the left of this figure. The lower curve is a more or less arbitrary smooth plane curve we call the tangency curve tau. The set of all tangent segments of constant length defines a region bounded by tau and an upper curve called the free end curve sigma, traced by the tangent segment's other extremity. The exact shape of this region depends on curve tau and the length of the tangent segments from tau to sigma. We refer to this region as a tangent sweep. When each tangent segment is translated parallel to itself to bring the points of tangency together at a single point, the set of translated segments is called a tangent cluster, as shown on the right of the diagram. When the tangent segments have constant length, the tangent cluster is a circular sector whose radius is at constant length. Here is Mamicon's theorem. The area of a tangent sweep is equal to the area of its tangent cluster, regardless of the shape of the tangency curve. Animation reveals why the theorem is true. The power of Mamicon's theorem is the wide scope of its applications. Here's an example involving a tractrix. A tractrix is the trajectory of a toy on a taut string being pulled by a child walking along a fixed straight line. A classical calculus problem is to find the area of the region between the tractrix and the straight line. To solve this by calculus, you need to know the Cartesian equation of the tractrix, which is not a trivial problem in itself. Then you can use integration to find the area. But with the use of Mamicon's theorem, the problem is easily solved geometrically as shown in this diagram. The region under the tractrix is a tangent sweep produced by tangents of constant length, say k, the length of the string. Its tangent cluster is a quarter of a circular disk of radius k. The cluster has area pi k squared over 4, so that is also the area of the region under the tractrix. Here's the idea shown by animation. Now here's a generalization of the tractrix problem that cannot be solved using calculus, but which is trivial by Mamicon's theorem. The front wheel of a bicycle traces out one curve, while the rear wheel, at constant distance from the front wheel, traces out another curve. What is the area of the region between the two curves? This region is a tangent sweep, so its area is also equal to the area of its tangent cluster, part of a circular sector, depending only on the length of the bicycle and the change in angle from its initial position to its final position. To solve this with calculus, you would need to know equations for the bicycle tracks. By Mamicon's sweeping tangent method, no equations are needed. You might add, and rightly so, the regions swept by tangents of constant length are very special. But Mamicon's theorem is also valid when the tangents have variable length. In this diagram, we still have a tangent sweep, as shown on the left, and this tangent cluster, where the tangent segments are translated so their points of tangency are brought together at a common point. Again, we have Mamicon's theorem. The area of the tangent cluster is equal to that of its tangent sweep. In a more general form of Mamicon's theorem, the tangency curve need not lie in a plane. It can be any smooth curve in space, and the tangent segments can vary in length. This animation shows an example. The tangent sweep will lie on a developable surface, one that can be rolled out onto a plane without distortion. The tangent cluster lies on a conical surface whose vertex is the common point. Again, the area of the tangent sweep to a space curve is equal to the area of the tangent cluster on the conical surface. By the way, we could also translate the tangent segments so the other endpoints are brought to a common point like this. The resulting tangent cluster is a symmetric version of the other one, and Mamikon's theorem is still valid. Now, to show you the power of Mamikon's theorem, let's find the area under the region of an exponential curve. Say y equals e to the x over b, where b is a positive constant, from minus infinity up to any point x0 on the x-axis. The tangent segments to an exponential are not of constant length. However, it is known that the projection onto the x-axis, called the subtangent, always has constant length, the constant in this case being b. In fact, exponential curves were first introduced in 1684 when Leibniz posed the problem of finding all curves with constant subtangents. The solutions are the exponential curves. In this diagram, each tangent segment is translated so the endpoint on the x-axis is brought to a common point. Because the subtangent is constant, the resulting tangent cluster forms a right triangle, a base b, and altitude e to the x over b, as shown by animation. So in this diagram, the area of the blue region is equal to the area of the yellow triangle. Therefore, the area under the exponential from minus infinity to x, the blue region plus the yellow triangle, is twice that of the triangle, which is a rectangle, a base b, and altitude e to the x over b, with area b e to the x over b. This argument evaluates the following integral geometrically. In chapter 1 of our book, it says that the integral from minus infinity to x of e to the t over b dt is b e to the x over b, the area of a rectangle. In chapter 1 of our book, we show that Mamikon's theorem also leads to geometric evaluations of many other integrals. For example, the integral from 0 to x of t to the r dt is x to the r plus 1 over r plus 1 for any real r except minus 1. And for when r is minus 1, it's the natural logarithm of x. Now I'd like to turn to some problems involving volumes of solids that can be treated geometrically with the help of Mamikon's theorem. These are not in our book. I will start with a class of solids obtained by sweeping a plane region tangentially around a cylinder. Take a plane region S between two graphs in the same half plane. In this figure, the x-axis is oriented vertically pointing down, and the y-axis is oriented horizontally pointing to the right. If we rotate S about the x-axis, we obtain a solid revolution swept by S, part of which is shown here. Now we place the x-axis along the generator of a general cylinder, not necessarily circular or closed. Keep the upper half plane tangent to the cylinder and move it tangentially along the cylinder as suggested here. Then this generates a tangentially swept solid. We call it solid tangent sweep. The corresponding solid tangent cluster is that obtained by rotating S about the x-axis. This figure shows a typical cross-section cut by a plane perpendicular to the x-axis. The area of the shaded band outside the cylinder is the difference in areas of two planar tangent sweeps of the profile of the cylinder. The area of the portion of the adjacent circular annulus swept about the x-axis is the difference in areas of the corresponding planar tangent sweeps, clusters. So, by Mamikon's theorem, the shaded band and annulus have equal areas. In other words, horizontal cross-sections of the solid tangent sweep and the solid tangent cluster at any height have equal areas. Therefore, by the slicing principle, the solids have equal volumes, which proves the following theorem. The volume of the solid tangent sweep does not depend on the profile of the cylinder, so it is equal to the volume of the solid tangent cluster, a portion of a solid of revolution. By varying the region S and the cylinder around which it is swept, we can generate infinitely many families of drilled solids of equal volume. We begin with solids swept around circular cylinders. Take region S to be a semicircular disk tangent to a circular cylinder of given height. Its solid tangent sweep is part of a sphere with a cylindrical hole. Its solid tangent cluster is a solid sphere whose diameter is the height of the hole, the height of the cylinder. They have the same volume. Now vary the radius of the cylinder and keep its height fixed. You get a family of cylindrically drilled solids that we call bracelets. All these bracelets have equal volume, each equal to the volume of a sphere whose diameter is the height of the cylindrical hole. It comes as a surprise to learn that the volume of each bracelet depends only on the height of the cylindrical hole and not on its radius or the radius of the drilled sphere. By changing the sweeping region S, we can generate all kinds of bracelets of equal height and equal volume. For example, if S is a semi-elliptical disk, you get a family of ellipsoidal bracelets. Each has volume equal to the limiting case of an ellipsoid. If S is a segment of a parabola, you get a family of paraboloidal bracelets, all having the same volume as the limiting paraboloid of revolution of the same height. These hyperboloidal bracelets are obtained by taking S to be a double right triangle, as shown. Each has volume equal to the limiting case of the cone. Animation shows these bracelets being swept by a double triangle. In all these examples, the solids in each family have equal volume because corresponding horizontal cross sections have equal area. Consequently, by simply slicing any such family by two horizontal planes a given distance apart and applying the slicing principle, we can produce infinitely many new families with the same property. The material on solids tangentially swept around cylinders is part of a joint paper Mamikon and I have submitted for publication to the American Mathematical Monthly. This paper also contains many examples when the cylinder is not circular. A sequel to this paper extends the ideas further by sweeping around other surfaces besides cylinders, cones, for example. The moral of this story is that there seems to be no end to the possible applications of Mamikon's sweeping tangent theorem. Finally, I want to thank my colleague Mamikon Natsakanian for preparing all the images used in this talk. He also prepared more than 1,000 color illustrations for our book. I would also like to thank him publicly for introducing me to his method of sweeping tangents. As a teacher of calculus for many decades, I was stunned to learn that many calculus problems could be solved more easily by using Mamikon's theorem. And as a special message to the undergraduates in this audience, you should know that Mamikon discovered his sweeping tangent theorem and many of its applications while he was an undergraduate physics major at the University of Yerevan in Armenia. Let that be an inspiration to you. Go and do thou likewise.
Are there any questions or comments? If not, let's thank the speaker again.